Good morning, everybody. I'm Mark, and I'm here with Matt, Ishan, and Rudy on behalf of the Metro Measurement Solutions team. So today we're going to be doing a project overview of our coordinate measurement machine. We're then going to look at our final design and then break it up into various mechanical and electrical subsystems which are included. We'll then talk about some of the challenges and opportunities that we have to improve some of the designs. Do a brief summary and then open up for any questions that you guys may have. So the main goal of this machine is to be able to collect measurements of the surface of an object and then export the data in some useful format. Through automation, the goal is to make measurements a little bit faster and more efficient compared to traditional manual measurements. It has applications in quality control in regards to making sure tolerances are within specifications, as well as reverse engineering, which would provide data and measurements for later analysis. So there's a lot of different available methods of measuring, including mechanical systems using photos and then also lasers. We decided to go with a mechanical system with a horizontal arm design. So this design includes 2 linear actuators for the vertical and horizontal movement. These actuators allow us to have 2 out of the 3 degrees of motion that are required to fully define a 3-dimensional object. The 3rd degree of motion is going to be supplied by a rotating platform here, which the object will rest on. These 3 subsystems will combine together to provide a cylindrical coordinate system for collecting data. So in our final design, you can see our vertical and horizontal actuators, as well as our rotating platform. Sitting on the platform is our standard, something that we use for measurements and testing, for repeatability and accuracy as well. At the heart of our machine is going to be our mechanical touch probe attached to the horizontal arm there. This was designed so that we could collect our data points, and will be discussed a little bit further in our presentation. But the way that the data points are collected is the mechanical touch probe will approach the object, touch off on it, and then the machine will recognize that it has touched off on the object, record the current position of it, and then repeat that movement. So it'll start at the top of the object and go down, and once it's completed the full line down the object, the rotating platform will rotate at a user-defined resolution. That will continue until the full object has been rotated all the way around and we can fully define the object. So the mechanical subsystems are going to be described a little bit further into detail by Ishan.
Thank you, Mark. I will further talk about the mechanical systems of our machine. There are 3 main components in our design, as Mark mentioned: the linear actuators, the rotary platform, and the probe system. Each of these systems help in collecting coordinates in the 3 directions, as Mark mentioned, from our cylindrical coordinates. I'll begin by talking about the linear actuators. The linear actuators help us achieve motion in the horizontal direction and the vertical direction of the horizontal arm. The horizontal motion helps us collect data in the R direction, and the vertical motion helps us collect data in the Z direction of our cylindrical coordinates. As you can see here, each of the linear actuator consists of a timing belt and pulley system, a stepper motor. This is for the horizontal one, and the vertical one is placed somewhere down here. A 3D printed carriage and cam roller system. This is how we achieved our motions in the horizontal and vertical directions. Moving on to the rotating platform. The rotating platform is responsible for collecting data in the theta direction for our coordinate system. As you can see here, the rotating platform is comprised of an aluminum plate, 3 supporting legs that were machined, a timing belt and pulley system, and a stepper motor. You can also see that we have our standard, as Mark mentioned, that is used for testing purposes, and then a small offset that I'll talk about a little bit later. You can also notice that we no longer have a traction surface. This is because we needed more friction than the force exerted from the probe, but the traction surface wasn't giving us enough holding. Therefore, we decided to use a double-sided tape. We decided to use double-sided tape because it got us a solid fixture and avoided any interference from fixtures holding on to it. Last summer when I worked over at Isuzu, their CMM had standard fixtures, so the engine blocks that came in through the CMM already had standard dimensions for screws to go in, so the system won't move. Moving on to our probe, which was our, I guess, our bottleneck also for the machine. Here, as you can see, the probe acts as a push button. So as the probe moves towards a component, it senses the surface of the component and breaks the circuit that is within this housing, and then collects the point and sends it to the microcontroller. As you can see here, the probe comprises of a spring, copper shims, an inner piston-like piece, and an oil-embedded bearing, and then the stylus over here. After testing, we realized that the movement that was needed to sense the point was 0.01 inches, and I used that through a dial indicator and tested it, I think, 20 times and checked the LED signal. I will now give it off to Mark to talk about our electrical systems.
Thank you, Ishan. As Ishan said, I'm going to be talking about our electrical systems. The first I'll be talking about our motor control, then our code with Arduino, along with our user interface, which was created using LabVIEW, and then I'll finish talking about how we created an STL file. So, our motors are all of our motors have a 1.8 degrees step angle, but they are connected to driver boards, which allow an eighth of that step for a final step angle of 0.225 degrees. This gives us a better accuracy when measuring our object. Our driver boards are then connected to our Arduino through the step and direction pins. What happens is whenever we want to take a step, we set the pin high, which tells our motors to take a step. We then put the pin low, to have the motors ready for the next step. Our directions pins are set high when we want the motors to go in the reverse direction, and then low when we want to move forward, giving us both forward and reverse movements. Our motors use two different voltages. Our horizontal rail and our rotating platform runs off 12 volts, and our vertical and probe motor run off 5 volts. And this is accomplished by our power supply. It provides multiple different voltages and at the currents we need for our motors. Next is our connectivity with our Arduino. Our Arduino is connected using a USB cable to our computer, and we use serial communication to talk to it through LabVIEW. This is accomplished through LabVIEW using VESA drivers. VESA drivers is a universal driver to allow LabVIEW to talk to external hardware, such as a microcontroller. Our Arduino is connected to our driver boards, as I explained earlier, through the step and direction. We also have limit switches. We have 2 limit switches on each linear rail and one in the probe to tell if the probe is in its horizontal position or vertical position. These limit switches will trigger an interrupt in our code to tell the motors to stop moving, so to know when we are at the end of our rails. Our probe is also connected to our Arduino using interrupts. When our probe is triggered, it sends a signal to the Arduino, triggers our interrupt, and then it records how many steps the motors have taken, which then are converted to distances, and then backs the motor off of the object so it can take the next measurement. This is our user interface. As you can see, we have a start and stop button. This allows the user to start and stop our machine for normal operation. While the machine stops, you can press the home button. This will home the machine. And we also have a pause and resume button seen here. This allows the user to pause the machine. It will save where it's at in the program, and then when you hit resume, it will pick up where it left off. You can also see we have our jog buttons. This allows us to manually jog each of our motors. And we also have LED indicators to tell when each of the sensors have been hit. We have a file path to allow the user to decide where they want the STL file to be saved. And we also have a progress bar to let the user know how far along in the process the machine is. Next is how we format our STL file. So once we get to, when we measure the object, it goes down the object and it collects somewhere between, like, depending on the resolution, it collects however many data points that is. It collects 2 of those, it then meshes those into triangles, and then it has to be output into the format as you see here. Others will cause errors when opening the STL file. So, and you get a triangle like this. And we have to do that all the way around the object. Next will be Rudy, who will talk about our challenges and improvements.
Thank you so much, Mark. So some of the challenges that we faced throughout the entire design process and construction of our coordinate measurement machine had to revolve around the process of data acquisition. The first one being LabVIEW. LabVIEW was a piece of software that our electrical and computer engineers on our team were not fully accustomed to. It's been a few years since we've been able to actually use it within some kind of environment, and we had to go back into research on the power and more specifically the limitations of what LabVIEW had to offer in terms of serial communication, which I will be talking about momentarily. The next thing was our probe, and electrically it was a normally closed push button. So that was kind of simplistic enough for us to understand on the circuitry side. But mechanically, we wanted to get the probe to be as light of sensitivity as possible. And with that, we had to take into account the sensitivity of the spring and the tolerance between the internal bushing and the inside piston. We wanted this to be as light of sensitivity as possible, so that way we did the measurement of the object without damaging the object or knocking the object over from a rotating platform, which is also why we use double-sided tape. Our third challenge was the microcontroller. We originally used the Texas Instrument MSP 430 microcontroller because it was a microcontroller that we were accustomed to throughout the years here at Valpo. However, it was giving us a lot of issues when it came to serial communication with LabVIEW. There were not available third-party VESA drivers that we were able to find easily, and the coding itself was giving us major setbacks. So that's why we decided to make the transfer over to Arduino Mega. We were still having some problems with the Arduino as well. We had to learn the code, understand the programming language, because it was kind of relatively new to us, and having to transfer our code over from the MSP to the Arduino. However, it did make communication a lot easier. We were able to find third-party drivers that were, it just made it seamlessly connect through the USB port, and we were able to work through serial communication through there. Some of the improvements that we would have loved to add if we were able to have a little bit more time and resources into our building of the machine was the GUI interactivity. So what we wanted to do was initially have a 3D image that would in real time build while it was measuring. This was a very early concept that we really wanted for our user interface, and we decided to kind of strip it down so that way we wanted to focus more on the main operation and be able to, we still wanted to show you the progress, which is why we left the progress part in there, but instead we decided to work on the main operation. The stylus offset was another big issue that we really wanted to see improved throughout our design process of the probe. Right now it is centered in the middle of the probe, and we would like that if we designed it to be on the bottom of the probe so that way we didn't have to offset our object. The last improvement we would have liked to add was to directly couple the motor under the rotating platform. And this was just more of a slight oversight that we saw throughout the design process. This would have allowed us to not worry so much and rely on the timing belts. If there was any issues with that, we would have no rotating platform. Thank you all so much. We will now open it up to any questions. We've been talking about our project review and giving you a manufacturing update. Any questions?
I didn't quite understand the STL file generating the look you had. You can elaborate a bit more about this. What do you mean by those triangles?
So the question is, there's a little more explanation on the triangles.
Yeah, in the STL file.
Yeah. So the STL file format requires it to be this way. It requires for each triangle you have to have a facet, normal, and an outer loop and in loop. And so each vertex, so right here, it would be this point here. And you have to do that for each of them, and that would create the triangle for it. And you have to do that for each triangle that you paint.
And each time you touch the object, you're creating a triangle?
Each time we touch the object 4 times, we create 2 triangles.
Okay.
You had a lot of issues with the probe binding as you touch. Do you have any ideas of how you would redesign the probe and avoid that issue?
So the question was how we would redesign the probe to avoid any of our challenges that we faced. One of the things I was thinking about was have the inner piston thicker so that we have more freedom when we have force from any point on that piece. Another thing, I was actually looking into more designs of the probes, and they're longer and thinner pieces, so have it smaller and more concise with a smaller sensitivity on the spring as well. And then I also found out a few laser techniques that we could have used, or limit switches that we could have used as part of our design, but this was the most basic design we could have used. Another thing would be have our probe sense in all 3 directions, so you can touch this way, up, and on the other side of it.
Why don't you have the probe rotate down so it would always move like out when it started? Why did you have to do that?
So the question was regarding the probe moving from a downward to a perpendicular position. So the way that we record the objects, to get the top of the surface of the object, the probe would get in the way of itself. So we designed it so that it would either be in an upright or a perfectly flat position, or it could rotate down 90 degrees so that we could collect the data points on top of the object as well.
So how would you know to tilt that surface in top?
It's in the process of how we have it coded to record the data. And then we know whether or not it's in the outright or down position via a limit switch.
So basically, it would keep going when it didn't sense anything, it would